Hi, let's get started with the Introduction to Hadoop Distributed File System lesson. In this lesson, you'll learn about the Hadoop Distributed File System, or HDFS, and its basic concepts and components. A Hadoop cluster is made of master and worker nodes, which are physical servers that are used for both distributed storage and distributed processing of massive amounts of data. HDFS is fault-tolerant. Therefore, detection of faults and quick and automatic recovery from failures is a core architectural goal of HDFS. HDFS stores large files. It breaks those files into blocks, which are then replicated 3 times and distributed across different nodes in the cluster. Redundancy yields fault tolerance. If a server fails, the other 2 servers automatically take over its workload. HDFS supports MapReduce and Spark processing frameworks. HDFS is scalable. If you need more storage or processing resources, you simply scale out instead of scaling up and add more nodes to the cluster. Finally, Hadoop doesn't require expensive, highly reliable hardware. It is designed to run on clusters of commodity hardware. Let's look at a simple example of a high-availability cluster. It is made of master and worker nodes used for both distributed storage and distributed process of the massive amount of data stored in the cluster. The NameNode Daemon, also known as service, runs on the master nodes on the HDFS side of the cluster. The NameNode holds the metadata about the cluster and manages the data storage. HDFS also contains worker nodes that run the DataNode Daemon or service. The data is stored in process on the worker nodes. There is usually one DataNode Daemon per worker node in the cluster. A DataNode Daemon manages the storage attached to the node that it runs on and communicates with the NameNode. On the processing side of the cluster, we have Yarn and the master nodes that run the active and standby resource managers. We will cover Yarn, MapReduce, and Spark in later lessons. HDFS High Availability, or HA deployment, addresses the single point of failure of early Hadoop by running 2 redundant master NameNodes in the same cluster to provide a fast failover if needed. The active NameNode is responsible for all client operations in the cluster. The standby NameNode acts as a hot backup to the active NameNode, maintaining enough system information to provide a fast failover if needed. Let's go over the HDFS concepts of files, blocks, and replication factor using a simple example. A client is writing a movieplex1.log file to HDFS. The file size is 350 megabytes. When HDFS ingests the file, it breaks it up into 3 blocks or chunks A, B, and C. Assuming that the default block size is 128 megabytes, blocks A and B are both 128 megabytes each, whereas block C holds the remaining 94 megabytes. The 3 blocks representing the log file are replicated to different nodes in the cluster using the default replication factor of 3. Replication increases availability and increases opportunities for data locality. It is more efficient to move the computation closer to where the data is located rather than moving the data to where the application is running. The NameNodes store file system metadata such as file name, size, replication factor, and access rights to the files, file blocks information and locations in the cluster, total number of files in the cluster, and total number of data nodes in the cluster, and much more. DataNodes use local disks in the commodity servers on which they run for persistence. All the data blocks are stored locally, which improves performance. DataNodes serve read and write requests from clients. They perform block creation, deletion, and replication based on instructions from the NameNode. DataNodes report their status to the NameNode by using heartbeat messages and Blockreports to detect and ensure connectivity between the NameNode and the DataNodes. Receipt of a heartbeat implies that the DataNode is functioning properly. A block report contains a list of all the blocks that are available on a data node. When a heartbeat is no longer present, the NameNode assumes that the data node is no longer functional and it unmaps the data node from the cluster and keeps on operating normally. When the heartbeat for the data node returns or a new heartbeat appears, it is added to the cluster transparently without the user's intervention. Let's go over the example of writing a file to HDFS. This example uses the movieplex1.log file that we used earlier. The client communicates with the NameNode and requests to write the movieplex1.log file in the file system's namespace with no blocks associated with it. The NameNode checks to make sure that the file does not already exist and that the client has the right permissions to create the file. If these checks succeed, the NameNode makes record of the new file. Otherwise, file write fails and an error message is displayed. The NameNode checks the available nodes in the cluster and determines where the blocks and replicas will be written. HDFS supports creating data pipelines. A data pipeline is a connection between multiple data nodes that exist to support the movement of data across servers in the cluster. A client application writes a block to the first data node in the pipeline. That data node takes over and forwards the data to the next node in the pipeline. This process is continued until all replicas are written to disk. In this example, a pipeline is created between the three data nodes and block A is written to data node 1. When block A is written successfully to data node 1, it is replicated and written to data node 2 and then to data node 3. Therefore, the data is pipelined from one data node to the next. The same pipeline process is repeated for block B, and the same pipeline process is repeated for block C. When each block is replicated successfully to the assigned data nodes, acknowledged messages from the pipelines are sent back to the client to communicate that the blocks are copied successfully. This diagram illustrates rack awareness in HDFS. The placement of replicas is critical to HDFS reliability, availability, and performance. For the common case, when the replication factor is 3, HDFS's placement policy is to put one replica on one node in the local rack, another on a node in a different rack, and the last one on a different node in the same remote rack. To access the NameNode web UI on the Oracle Big Data Lite VM, click the Start Here icon on your Big Data Lite VM desktop. From the web browser toolbar, select Hadoop NameNode. The NameNode web UI is displayed. The NameNode exposes its web UI on port 50070. You can use this page to display useful information such as the number of files, directories, and blocks in the cluster. In this lesson, you learned about the Hadoop Distributed File System. You also identified HDFS design principles, characteristics, and components. Thanks for watching. Learn more at docs.oracle.com/en/bigdata.